So I'm going to be talking about Dask-Gateway. So my name is Jim Crist. I work at Anaconda. I've been here for about 5 years now. Started when we were just Continuum. Quick show of hands. How many of you have heard of Dask before? Oh, excellent. How many of you have used Dask before? Okay, cool. All right, so for those of you that don't know, we'll start with a quick overview and then we'll move on to what we're going to be talking about. So Dask is a flexible parallel library, or a flexible library for parallel computing. Provides a familiar API for writing scalable analytics using the PyData ecosystem. So we have Dask Array, which looks a lot like NumPy. Dask Data Frame looks a lot like Pandas. Dask ML looks a lot like scikit-learn. These are mostly drop-ins. If you're used to using one, the other should usually work for you with little change to your code. It's designed to scale from a single machine to a large distributed cluster. Your same application code should be able to run usually in multiple contexts with only a couple changes to how you're deploying it. At a deeper level, it looks a little like this. User writes some code. This is using Dask Data Frame, which looks a lot like Pandas. Read some CSVs, do a group by, whatever. Familiar looking Python code. Behind the scenes, Dask generates a task graph. This is a description of the computation. This is a set of tasks that need to be done in some order, and they can usually be done in parallel. And then Dask schedules those tasks across a cluster. So here we have a scheduler and a bunch of workers. These tasks can be distributed throughout that based on the scheduler's logic. Delving into that last bit a little bit more, this is what the cluster looks like at a lower level. We have a scheduler. The scheduler is in charge of managing all of the things that are going on at the time in the cluster. The scheduler says where tasks should run. It manages communication with workers. It finds dead workers and reruns tasks. And it also talks to a client. The client process here isn't on the cluster. That's what's living in your script, in your notebook, whatever. That's on the user's end of things. The scheduler and the workers live somewhere else in a cluster. One of the hardest parts of distributed computing is how you actually end up with one of these. How do you deploy your code? How do you actually interface with the backend? So we have a whole stack of things that have to go on here. So we have in Dask something we call a cluster manager. This is an object that exists in your Python code. It deploys a scheduler and many workers by talking to a resource manager. Resource manager is anything from Kubernetes to Yarn to, if you work in a place that might have an HPC system, you might be familiar with Slurm or PBS. This is the thing that actually gives you resources. This is the thing that gives you memory and cores to run your processes on, figures out what node of a cluster to run things on. And then that's all either in the cloud or on a physical hardware, but local, but it needs to be running on a computer somewhere. The cloud is computers, they just might not be yours. So we have a whole tier of abstractions that we need to work with here. This talk is mostly going to be focusing on this bit. So cluster manager is the thing we have in Dask. It's a Python object. It's a base class, actually, that you can implement with many different backends. So Dask provides ones for Kubernetes with the Dask Kubernetes project, Yarn with Dask Yarn, HPC job queues, Dask job queue. We have a newish one for doing cloud native stuff, so it'll deploy directly on EC2. Standard interface, you create an object. It's got two methods: scale. You pass in a number, it scales, it gives you that many workers, and adapt. You can say, I want to adaptively scale between a min and a max. And that'll look at your workload and it'll say, if you could use more workers, it'll try to give them to you. And if you don't need as many workers, it'll scale down. It helps you not use too many resources. Anyway, standard duck type interface, create a cluster, it works. Example code might look like this. This might be a script or part of your notebook. You import from a backend. Here we're using Dask Yarn. So from Dask Yarn, import Yarn cluster. We create a cluster object. We ask for workers. When we create a cluster object, we pass in things that might be specific to the backend. So here we're saying what Python environment we want to use. We want to have 2 cores per worker and 8 gigs per worker. Then you connect. And you write your application code. You're connected to the cluster. Everything else transparently runs on that. The only part that's specific to the backend, in this case Yarn, is this bit. Everything else is generic. It would work with any other cluster manager. As I said before, we have different ones, so you just swap out those lines for creating a kube cluster instead, or a PBS cluster. So that's the status quo. That's how things have been working in the past. There's some nice things about this. So deployment is part of users' code. There's no need for extra CLI tools. There's no Spark submit for Dask. You create your cluster in your script. You run your code. It shuts down when your script ends. It can work just from scripts. It can work from notebooks. Can be part of a larger application. Deployment as part of code is got a lot of nice features for it. There's no need for extra infrastructure. All of these projects are designed to work natively with the backing resource manager. So for example, Dask Yarn integrates really well with the Hadoop Yarn resource manager. It plays with its authentication. You as a user can install this on your edge node and run without asking your admins to stand anything else up. They don't need to install extra infrastructure. They're all just Python libraries, so they're easy to install. They're a pip install or a conda install away. There's no need to reach out to other install mechanisms. And they're extensible by design. So this is a base class. Anyone can implement a new backend. If you have some fancy hardware we haven't implemented something for, you can write your own cluster manager, and it'll all just plug into the ecosystem. This also has some downsides. So each backend requires domain-specific knowledge. So as you saw in the Yarn one there, we were passing in environment stuff. If you were running on Kubernetes, you need to know what a Kubernetes pod looks like. This might be good for expert users, but not everyone has that knowledge. That's a little bit of a ramp up if you're switching between backends. Users must have permission and network access to talk to the resource manager. Because we natively integrate with them, you also need to have access to them. So for Yarn, this looks like you need to be able to log into the edge node. You need to have permission to run jobs. You need to have Kerberos set up. Kubernetes, you need to have permission to spin up new pods. If you're on a shared cluster, admins might not want to give that to you. And then you also have to have network access. Because of how our distributed system looks, you have your client, which lives in your code, and you have the scheduler, which lives somewhere else. There can't be a firewall in between you. So if you have a cluster, which has got ports that are locked off, you need to make sure that you have access to those ports, and you might have to ask admin to open a port. And we don't necessarily want to open a port for every single user in your cluster to have their brand new scheduler on. No central management. In small orgs, and actually in large orgs, depends on your team really, that might be fine, but many institutions want some way to audit what's going on with their system. You want to be able to see which users are using that many resources. With no central management, no central Dask server, whatever, you rely on the backend resource manager to do that. Depending on your resource manager, they might have plenty of facilities for this, or they might not. You might just get, I have a pod running and I don't know who started it. And it's hard to enforce good practices. You're relying on your users to be deploying with the proper configuration, using good practices for managing their resources, not leaving a cluster running for forever. And then clusters are also tied to the lifetime of the client. The current way where they're deployed as part of code, when you restart your notebook, you also end up restarting the cluster, which is both good and bad. Often that's what you want, but if you're trying to do a lot of iterative work, you can end up burning through a lot of resources accidentally. So this brings us to Dask-Gateway, which is our attempt to rectify some of these issues. This is just another alternative I want to stress. This is not saying that the other methods that we've talked about already are bad. This is just a different one. This is trying to solve those things. There are pros and cons. So Dask-Gateway is a larger architecture system. It's got a server that admins need to deploy somewhere. Architecture looks like this. You have a cluster. It's got a firewall around it. Most clusters do. You have a process that's running the gateway server. It's got some proxies on it that just runs somewhere in your cluster. Users connect to it through a port that's exposed in the firewall, and they're given Dask clusters as a service. It uses a REST API, so users are making REST calls to say, give me a cluster, connect me to that cluster, scale it up to n nodes, what clusters do I have? Everything is authenticated and secure through a single port. And users don't need to have direct access to the backing system. You don't need to give them Kubernetes permissions or Yarn permissions. This is all handled by the server. As I said, there's a REST API for managing clusters. We have a couple proxies that are implemented as part of this. We need to be able to proxy Dask scheduler traffic through. So between the client in your code and the scheduler that's running on the distributed system, there's some communication. We need to be able to proxy many of those through so that all users are talking through the same port. We also have a proxy for the dashboards, which I'll talk about in a bit. It's a flexible design. So just as before with the old cluster manager design, where we had different backends, Dask-Gateway supports different backends. It was really important that we weren't limited to running just on Kubernetes or just on Yarn. So we support all of the same ones that we support in Dask natively, but with this larger server model. And it's also got configurable authentication, so it plays well with Kerberos, plays well with, if you're deploying Jupyter Hub, we can plug into their authentication. There's a couple others. And most actions are done server side. So the gateway server, this bit, handles most of these things, so you can enforce good practices. You can enforce that users are turning on adaptive scaling. You can enforce that users' clusters scale down after a certain amount of time. You can set resource limits. Using Dask-Gateway, so here's our other example. We're creating a Yarn cluster. This is the one from before. If we were to do this with Dask-Gateway, we just swap out what kind of cluster we're creating, and that's it. The rest of our code stays the same. But now we're deploying on some admin run server instead of using the resource manager natively. Do a little bit demo. I think I need to make this bigger. Yeah, so the question is, at this point, the admin is, the user doesn't really care what it's backed by, and that's true. Yeah, we'll talk about that in a bit. Is this big enough for people in the back? Yay or nay? Cool. All right. So here I'm connected to, this just happens to be running on Kubernetes, and it just happens to have logged me out. Anyway, doesn't matter. So I'm going to deploy a gateway cluster. So from Dask-Gateway, I'm employing a gateway cluster, and I'm just going to create it. It's going to scale up. And now I have a cluster object. Just like if you're familiar with Dask, all of our cluster managers have this really nice IPy widgets GUI. So if you're working in a notebook, you can do scaling with the GUI instead of calling scale manually. So here I'm going to scale up to 3 workers. And I should see them up here. And I can connect and then do some work. Here we have our dashboard. So Dask provides a nice dashboard for auditing what tasks are going on. So each row is a worker. Each box is a task. So that's a sum task. Here we're doing a normal operation. And then X is time. So you can see what's going on. This is being proxied through. If we go back up, we have a proxy here for proxying through the dashboard traffic. So the dashboards run on the scheduler. We're proxying the HTTP traffic through to the users. So you only need to have a single port open for users to get access to the dashboards. If instead I wanted to adaptively scale, maybe I want to scale between 3 and 0 workers. Since I have no tasks going on right now, I should see that drop off pretty quick here. Yep. But I can run my code again, and I should adaptively scale back up. So this is really nice if you want to make sure that your users are not keeping resources when they're not using them. They might be, a lot of writing and analysis code is thinking. When you're thinking, you don't necessarily need to be using resources. So here we adaptively scaled back up to run our tasks again, just long enough to get a response, and then we scaled back down. Quick question. I have, the question was, have I showed the ability to create a local cluster?
So Dask has the ability to create a cluster, a scheduler, and then let other things link into it. But here you're showing on top of Yarn, correct?
This is on top of Kubernetes, but this is using Dask-Gateway to manage it. I don't fully understand the question. I'm sorry.
I know Dask can create on its own without any system underneath. It can create a cluster.
Mm-hmm.
I've done it myself, just by Dask and the content. That's it. What's the difference here?
The difference here is where it's deploying. So here we're using the gateway cluster to deploy remotely, talking to a server. We'll come back to your question later. I'm sorry. Anyway.
My understanding is that this did not. We previously provisioned GCP resources. So this did not create the Kubernetes cluster.
Yeah. We'll get to questions at the end. I'm sorry. So besides just having a gateway cluster object, we also provide a gateway client. So Dask-Gateway allows users to keep long-running clusters up. We don't necessarily shut them down at the end of a notebook. So you can list what clusters you have. Here I have one. It's the one I'm connected to. Provides a couple other methods on here. I can connect to a running cluster. So if I wanted to connect to the last one here, I can reconnect to a cluster that's been running for a while. Shut that down. If I wanted to be able to change options, so one thing that people really wanted that Dask-Gateway provides is the way to lock down options. So in the previous model, you have to give, say we're running a Kubernetes, you have to give your users permission to launch Kubernetes pods. They have to have raw access to the Kubernetes API, which means they can do whatever they want in your cluster. For large organizations, that's not something they might want. You might want to be able to lock down what features the user can do. Maybe you don't want them to be able to change what image they're using or pod security policies. Since everything is running that's talking to the Kubernetes API is running on the gateway server, which the user doesn't have access to and admin has deployed, admins can lock down what options a user has access to. So here we can see what options a user has access to by calling cluster options. This is going to query the server to see what the admin has exposed. By default, the admin has exposed nothing. Here we've set this up to expose worker cores and memory, so that a user can configure their cluster to use 4 cores per worker instead of 2 by default, or a different memory or a different image. But nothing else they have permission to change. Oh, nope. You can also set limits on these. So this is a mapping type object. I can try to change worker cores to 20, and it's going to give me a nice error that says worker cores must be less than 4. I got 20. This is checked both client side for nice errors and then server side too. So users can't hack around that. If there's no quick questions, I'm going to go back to the presentation. Cool. No. Yes? Yeah, so the question is about pushing custom environments to the workers. So Dask-Gateway provides a lot of plugin aspects here, so you could handle that yourself. Exposing things it's just a single handler that's configured. And well, actually, I'm just about to delve into configurations. We can talk about that. So moving back to the presentation. Cool. Additional features we didn't talk about, resource limits. You can set resource limits. You can say a user gets no more than 100 gigs of memory or 20 cores or whatever, and they're free to distribute those throughout workers how they want, but they don't get to use more resources than they're allowed by the admin. We can automatically shut down idle clusters. You can set a timeout and say if the cluster hasn't been used to compute anything in 15 minutes, kill it. User can restart it. That helps stop resources from being used longer than they need. And it's got strong interop with Jupyter Hub. So if you're deploying Jupyter Hub, we can integrate really nicely with it for auth, for plugging into its various configuration settings. And then there's a couple other things. Internals. So the rest of this talk, we're going to be talking about the internals. There's a couple interesting bits that I think are worth mentioning. And that also highlights some of the architecture. So first, configuration. So like any server, we needed to be able to pick a configuration format. We needed some way for admins to say what backend to use, what ports to run on. So we could use static files like many projects use, YAML, JSON, TOML. We didn't use any of these. So YAML's got some weird edge cases. This is something I found the other day. YAML supports something called sexagesimal numbers, which is a numbering system used in ancient Sumeria. And it can lead to MAC addresses being converted to numbers depending on what they look like. So it's not the most consistent format. Static files also have issues. They're not configurable at runtime. So say you're deploying on a system and you want to use the host name that's on the system. You can programmatically get that, but you'd have to statically configure it in YAML, or we'd have to build that into our YAML spec for configuration. And we'd also need to write our own validation if we're using these kind of formats. So instead, we went with a cool little project called Traitlets. Traitlets is a Python library. It provides declarative configuration with automatic validation. Configuration is done as code. I'll mention what I mean in a second. And it's the same configuration system that's used by the whole Jupyter ecosystem. So if you ever tried to add plugins or configuration to IPython or Jupyter Notebooks, it's the same system. So here's what Traitlets looks like. If you're writing code with Traitlets, you create a configurable object. you define a couple attributes on it. So here we're defining a configurable width with the default value of 1, minimum value of 0. Little help, this shows up in descriptions and queries and docs. And then we're saying that, yes, this is configurable. We do the same for height, and then you can use the attributes down below. So here we're defining area is width times height. To configure it in a Python file, you can use Trailets configuration is done using Python syntax. There's an automatic C variable that is a config object that's injected to this file before it's run. And then you set config values on it as attributes. So here we're saying c.rectangle.width. This is setting the width attribute of a rectangle default to 10. So going back up, this is a configurable object. We had width and height as configurable variables. Trailets config looks like this, where you just add c dot whatever the class name dot whatever the attribute equals something. Because this is just Python, though, you can do whatever you want with it. So, oh, I got a little ahead of myself. In the code, then you load the config object, and it loads the defaults, and you have full access to them. Because it has automatic validation, I set the min before as 0. If I try to set something under 0, it's going to give a nice error. I didn't have to write any of the validation code myself. Trailets just does this for you. And because it's just Python code for configuration, I can do complicated things. So say we wanted to support wider rectangles on Windows. You can query just using Python libraries to do that. So this has been really powerful. This has allowed us to integrate well with other config systems. So we have a Helm chart, and we're able to pull our config on Helm from a config map programmatically in a Python script and then load it with Trailets, rather than having to build in support directly to Dask-Gateway to read a Helm config map. We support configurable backends, as I mentioned. So the example demo I showed was running on Kubernetes, but we support Yarn, we support JobQ, PBS, Slurm type systems. We need a way for the admins to configure those. You need a way to specify what backend you actually want to run on. So the way we did that was we abstracted all of the backend specific things out into a base class, which we're also calling a cluster manager, which is a little confusing. And then we implement that class for various backends. So we have a Kubernetes cluster manager, we have a Yarn cluster manager implementation. And then the backend class is configurable using the trailets type traitlet. So just as I assigned width equals a float before, we're using a type 1 here to have a configurable class. Base class, it's got a couple standard methods on it. Start cluster, cluster status, stop cluster, same for workers. These can be defined for probably any backend system. If you can run a process, you can probably define these standard things. So this is also extensible. You don't have to have built-in support. So just as before with our previous status quo method, if you have some custom hardware, if there's a backend we don't currently support, you as a user, as an admin, can write your own base class here, or your own cluster manager implementation, and plug it into Dask-Gateway, and everything should just work. Cool. And then this shows configuration. So here we're defining to use the kube cluster manager, same as trailets before, just it's Python code. We assign the class, and then we configure attributes on the kube cluster manager instead of the Dask-Gateway. Any quick questions about trailets? Yes, yeah. I'm just covering, this whole part of the talk is just things I think that are useful outside of Dask-Gateway. This is things I learned while writing it. So trailets is a nice library. I recommend people use it. It's good. I'm sorry, say that again? Yeah, so the question is, can you put arbitrary Python code in there? Yeah, the answer is yes. This is a Python script. All that's done is that a C variable, which is a config map, is injected into the namespace before this is run. So you have a variable that already exists called C. Everything else is you can do whatever you want. Yeah, the statement was it's dangerous. It could be dangerous. The rule here is that admins should be doing this, and users shouldn't have a way to write over this. But it also is powerful. It allows a lot of nice behaviors that, yeah. Any other quick questions on this before I move on? Cool. All right, another thing. So there's a scheduler proxy component of this. So Dask uses raw TCP to communicate. Most proxies are either level 7 proxies. They proxy HTTP, so they can dispatch on the path of the HTTP request, or they proxy TCP to a static address. We wanted to be able to dispatch, but we also wanted to be able to use TCP in the proxy. We also actually wanted to encrypt this too. We want to make sure that our traffic is encrypted so that we're secure. No one can be sniffing what kind of data you're passing around. We could include a custom protocol. So in our messages that we're passing between the Dask client and the Dask scheduler, we could include something to dispatch on, but that would require our scheduler proxy to decrypt the message to figure out what we're routing to. So the solution was to use something called the server name indication. This is part of the TLS spec. It's a little header that's part of the handshake that's unencrypted that can be used to pass in something like a server name, which is what many proxies use this as. Or in our case, it's a cluster name that we're going to route to. And it allows routing TLS encrypted traffic without decrypting it, but just looking at the unencrypted server name in the handshake. So the basic loop in the scheduler proxy is on each connection we get, we pull out the SNI, the server name indication, from the handshake. We check our routing table. We see if we have one. Then we just replay the entire connection on another socket. And the rest of the proxy is just copying bytes from one socket to another, which is very, very fast. We don't have to do any TLS decryption. We don't have to do anything complicated. We're just routing. This is all written in Go because I needed to do some low-level bytes handling. It's good support for handling many clients. It's good async I/O. And the standard lib had a bunch of features that I wanted that made this easy to do. I also wanted to write Go. I hadn't done it before. And it's bundled in with the Python project. So if you haven't done this before, Setup Tools has a feature called package data, which allows you to bundle arbitrary files in with your wheel. So we just bundle in our little Go application as package data, and we can run it as part of our code. This makes it really easy for users to install. You can still pip install Dask-Gateway server, and you get the Go code bundled along with it. Testing. So as you can imagine, we have Kubernetes, Yarn, Slurm, PBS, local processes, probably adding more. We have a lot of different backends we need to test against. We also have different authenticators we need to test against, many different server features, client features. Our test matrix can get rather huge. We want our tests to be thorough, but also fast, and we want to make sure that we can actually test on all these backends. So the solution for the cluster backends was we have a generic test class. PyTest lets you write a test class, and then you can parameterize that on various other implementations. So we have a generic test class for testing a cluster manager backend that tests, say, start cluster works properly, start worker works properly. We walk through a bunch of standard workflows. We parameterize these on each backend, and then we run them in a Dockerized setup. So we have Docker containers that stand up each of our different Kubernetes, Yarn, PBS, Slurm. We have one for running each of those. If you're interested in how those work, I have a link here. These slides are going to be online too later. And then the tests are only run if they're needed. Travis CI has a feature for doing conditional builds where you can cancel branches that you don't need in a PR. So this allows us to run our tests pretty fast. Usually the Yarn code doesn't change every PR, but when it does, we can actually test the cluster backend still works. And in the main application, most of our server tests for server behavior run in one process. So we have an in-process cluster manager implementation that runs everything in async I/O tasks. This makes it really easy to inject failures. So we can kill workers arbitrarily, kill schedulers arbitrarily. Lets us make sure that our code is running robustly, but also keeps our tests pretty quick to run. And it also is really nice. You can use PDB if you're running everything in the same process to inspect global state. So what would normally be a distributed cluster, we have schedulers and workers and clients and the Dask-Gateway server all running as separate processes. We can run in the same process using async I/O and check global state is consistent. We use PyTest async I/O for async I/O tests. It's a great library. If you haven't written a lot of async code, I recommend using this if you ever have to for testing. Cool. Conclusion. So Dask-Gateway, which is what this talk is about, is a centrally managed gateway server. So this provides central managing of Dask clusters. Admins set things up once. Users can connect. They don't have to do anything complicated. They don't have to know anything specific about the backend. They can just request a new cluster. It's secure by default. Automatic TLS goes everywhere. No elevated user permissions. Users don't need direct access to the backend cluster. They just need to be able to talk to the gateway server. It's flexible. We support many different cluster backends, many different authentication methods. It's robust to failure, which I actually didn't get to, but you can kill the gateway server and restart it, and everything continues to work. So we can do nice, smooth upgrades, failover. It's designed with institutional members or teams in mind. The previous methods that I talked about at the beginning of this talk are still very valid, very useful, still recommended for many use cases. So this is not a replacement. This is another solution for cases that need it. I want to make that clear. Extra resources. So all of our docs are available at gateway.dask.org. We have nice installs guides for installing locally on a Hadoop cluster, Kubernetes cluster, HPC job queue. We have user guides. Yeah, hopefully our docs are thorough. And then if you actually want to contribute or ask issues, it's available at dask/dask-gateway on GitHub. And then we have our main Dask website. Questions?
So I have one clarification and one question.
Mm-hmm.
I assume that a user can use multiple clusters. Like if they have multiple notebooks with long-running jobs, can they kind of launch off different ones? Or
Yes. So yes, users can have multiple clusters. One of our user limit settings is a max clusters. So an admin can say users can have no more than 4 running concurrently.
and the total core limit will be a summation of that.
Yep. Yes.
What do you see the biggest thing that needs to still happen with Dask-Gateway, or like the biggest, the next feature that it really needs, or something like that?
Yeah. So the question is, actually, you have a mic, so I don't have to repeat it. That's great. The biggest thing that needs to happen is, so Dask-Gateway is a lot like JupyterHub. We cribbed a lot of their design. It's a great project. If you haven't looked at it, JupyterHub runs many Jupyter notebooks in the same way that Dask-Gateway runs many Dask servers. But we also inherited some of their weaknesses. So the main plan for the near future is to move to a multi-server model. So right now you can only have one gateway server running, as opposed to other web apps where you might run many of them behind a load balancer. The gateway server keeps a lot of internal state. It keeps it on a database, but it's not designed for concurrent server access. That's partly because we inherited from JupyterHub that limitation. That's partly because I'd never written a web application before and didn't really know what I was doing. So yeah, that's the near future design is to move things to make better use of the database for concurrency so we can run multiple servers.
So I'll phrase my question from before, because what you're showing here is that you're working through a gateway that talks to several other resource management systems, Yarn, Slurm, and so on. Dask on its own, just by if you launch a scheduler and you spawn workers, replaces this. The only thing it doesn't do is give you different users. And yeah, I'm not sure how much you can allocate resources or not, but in today's world, the old ways of actually creating clusters for users are going away because people just rent on the cloud a bunch of computers and use them. So specifically to this, are you going to go and develop Dask more so those systems are going to go away eventually? Or are you always going to support them to some degree and piggyback right on whatever they're giving? Or are they giving some functions that are very important that you don't want Dask to do?
Real quick clarification before I answer. Sorry, are the what systems going to go away? When you said systems,
I mean, the resource management system like Slurm is a resource management system. Basically, it gives you resources and creates a cluster for you. So you no longer need the creation of the cluster because Dask itself can create a cluster. Why are you I know that you want to serve them for now, but in the future, don't you want to inherit some of those things that they are doing and go in other directions? It's a long philosophical questions, but like, where are you going with this? Because Dask is already powerful on its own. Why are you supporting those old systems?
Because people use the old systems. So many like universities have a Slurm cluster. We want to make sure that things run well on them.
Some universities are not doing the smart things, that's for sure. So yes, there are some cases where you need to share resources, but the world is going to a place where you actually can isolate. You can create on virtualized machines that are only your own. You no longer need to manage the users as before. So you're saying that you're just because there's a current need, you want to support it?
I think that there are many different use cases for things, and I think that saying that across the board that a Slurm cluster is a bad thing is not necessarily something I would support.
So here's my, this is, I go back to a question. So give me a use case where actually this is needed. Like, and you don't want Dask to actually go and replicate some other system.
I think we can talk more after this. This is getting a bit away from the main talk. Thank you.
This might piggyback off that, but I'm currently using Spark environment, and I submit Spark jobs and everything. So I didn't know about this and wanted to know what are the differences, better or worse, from Spark, maybe performance or connecting to data.
Yeah. So I'm going to interpret your question as how does Spark compare to Dask rather than, okay. So Dask-Gateway is just for deploying. It runs the same everywhere. We have a whole page in our docs about the comparison between Dask and Spark. I recommend that you look for that. I can send you the link if you ask. In general, Dask and Spark solve the same problem. One will be more performant on some things, one will be more performant on other. One thing that we think that we do well in comparison is that Dask is more flexible. The backing paradigm is distributed acyclic graphs. Spark has a little bit more of a higher level structure on top of it. So you can do a little bit more raw task scheduling. That might not mean things to most users, but if you really need to reach out and do complicated things, Dask is more flexible. We also are written in pure Python, so you're going to get tracebacks that are in Python. You're going to get, it feels a little bit more like pandas than like a Spark data frame might. So.
Hey, first of all, thanks for all the work you're doing. We're trying to deploy Dask more and more where I work at, and right now we're stuck on using local cluster. And one of the reasons is that we don't have this like admin control. So if we're not allowed to just like deploy on Kubernetes or anything like that, we need to have an admin who can control access. So I think this sounds really, really useful for us. Have some kind of like rapid fire questions maybe, which is logging. Is that built in already? Or?
Yeah, so logging is an open question right now. There's an open issue. Every backend handles logging differently. We would like to be able to abstract that out in some way so we can have a generic log provider. Yarn does it for you. Like all Yarn jobs get logging for free. Kubernetes has a billion different solutions, it seems. Log is an open question. Dask does log. We just don't know what to do with the Kubernetes logs and where to put them.
Gotcha.
So.
And then for authentication backends, what kind of authentication protocols? I know Kerberos is in the settings. What about like LDAP or?
Yeah, so authentication protocols, we support Kerberos. We support plugging into Jupyter Hub, which can use. The trick here is this is a REST API meant for not humans talking over a browser. So we need to make sure that we support protocols that don't require human like in the loop. So that's why like Kerberos can do that with a ticket. We can do that by using the token that Jupyter Hub generates. But other things would require like a web type form, which is a little harder to play with. Authentication is another open question. What things should we support and what things should be pumped on? If there's something that you need, that'd be nice to talk to. Anyone else?
If someone was just getting started with setting up distributed workflow, do you think Dask-Gateway is the most sort of convenient way to attack that problem?
No. So well, it depends. If you're just trying to get started with Dask, I recommend using Dask locally. I recommend just creating a local cluster. You can do that by calling client with no parameters, and you're good to go. Everything just works. If you are trying to get things running remotely and it's just you, I also recommend not using Dask-Gateway. Dask-Gateway is mainly meant for teams. It's meant for admins that want security and auditing. It's meant for easing the burden on non-expert users. The person setting up Dask-Gateway still needs to be an expert user. But then other future users might not need to be. So, well, thank you.